We all set?
Take it away.
All right. Thank you very much, and good morning, everyone. I recently had the opportunity to do some analysis, both using conventional tools and using Pangeo, and I thought, well, maybe I can do a little compare and contrast. So there we go. So I am the data manager for NARCAP and also for NA Cordex, which is the North American branch of the Cordex program, which is a global program of downscaling global climate models using regional climate models to get higher resolution regional results. So I manage this archive that we've built at NCAR of the results from the simulations in this collection. And one of the things I do is, my main job for that is making this data useful to end users. So occasionally we get requests from people who say, hey, could you, help me get the data in a particular format or something like that. And in this case, I got an email from somebody who works for Deloitte, doing consulting for a client, and they were interested in knowing about freeze-thaw days, which is days where the minimum temperature is below -1 Celsius and the maximum temperature is above 0 Celsius. So you're crossing the transition. This is important for agriculture and also roads. There's a lot of people who are in logistics and things like that who are concerned about this, and they wanted to know hey, for your simulations in the NA Cordex archive that are 50-kilometer resolution, they were interested in getting data that was the annual average of the freeze-thaw days from 1950 through 2100, using the simulations that we've bias corrected, and they wanted data over the US and Canada, and they wanted ensemble statistics from 3 different groups of the models. So we've got, let's see, 1, 2, 3, 4, 5, 6, 7 models, no, 6 models that are run using the RCP 4.5 assumptions about future atmospheric composition, and another corresponding 6 models that are using the RCP 8.5, which is higher emissions scenario. And then we've got a half dozen models that don't have a corresponding RCP 4.5. So we only have RCP 8.5. And they said, we'd really be interested in having some ensemble statistics like the minimum, the maximum, and the median across the ensemble, each of these 3 ensembles for these groups of models. And I looked at that, and that's the kind of thing that I can, using tools I'm familiar with, bang out in an afternoon. So I often will do requests like that, just in the name of making this data more useful to people. So I said, sure, I could do that. And normally I use these command line tools like CDO and NCO, working with netcdf files that live on Glade, which is NCAR's big storage system. I'm familiar with doing that. I know how to use all these tools. I can do it pretty quickly. And I said, well, but why don't I also do it using a Pangeo notebook for our Science at Scale project? We've recently taken the NA Cordex collection and converted it from netcdf format to ZAR format so that we can put it in the Amazon cloud as part of their public data program. And ZAR plays real nicely with Pangeo and Xarray and Dask. It's well suited to being, parallelized in a very transparent fashion and to run efficiently that way. So I said, okay, great, let's do it both ways and see what the differences are. So using the command line tools, the way I approach this is using command file parallelism, which is you write all of your commands to a text file, and then you hand it to the scheduler for the supercomputer here at NCAR and say, please run each line in this file in, using a separate processor on the supercomputer. And so, it's the kind of thing where what you would normally, where you do a little for each loop in the shell and you write out all these command files, and then you send it to the scheduler. And, generally these things get scheduled and run pretty quick because each individual task doesn't take very much time. There's just a whole bunch of tasks in the aggregate, and they if you're doing them serially, it adds up. So the workflow doing it this way is, first I have to take minimum temperature and maximum temperature and put them into the same file. That was a reasonably expensive, that takes like a minute plus to run, just because these are very big files. It's 150 years of data, 150 years of daily data over all of North America, and at 50-kilometer resolution. So that's a fairly big file. It takes a good chunk of time to just read it in and write it back out. So that was the first step. And then we have to calculate the freeze thaw days, which is one line using NCAP2, which is the NCO command that lets you do arbitrary algebra on whatever's inside your file. And then things start getting a whole lot faster. So, then I have to take the daily data, sum it to get annual values. That's starting to go, so the calculating freeze thaw days takes about 18.5 minutes. But then summing up the daily data to annual data only takes 17 or 30 seconds, depending on whether they're talking about the historical data, which is 55 years, or the future data, which is 95 years. Combining those into one file, less than a second. Trim the ends because everything's, the different simulations don't all end on exactly the same date. Calculate the ensemble statistics, and then do some metadata cleanup. Those last steps are important, but they don't take hardly any computing time. So, running these on, we start out with 36 files, and then, once I've concatenated them, it gets down to 21, and then, cropping things gets faster and faster. All told, it took about 20 minutes to run this in parallel. That's of computer time. It actually takes a lot more time of me writing the commands and things and finding mistakes and fixing them. These statistics don't include how much time it took to send the job off to the scheduler and then wait for the scheduler to actually run the job. But that's pretty quick. These things get run fairly fast because they're small and they can fill in holes. And so it was about 20 minutes. The one other noteworthy thing is that this step where we calculate the freeze thaw days takes 18.5 minutes, as long as you run it on the analysis system where you can access a node that has 60 gigabytes of memory. So it wants a big chunk of memory to actually do that piece. So obstacles to doing it this way. CDO and NCO are complicated tools that require a fair amount of expertise to use. I'm very comfortable with them, but it took me a while to get there. And they've got a million options, and you need to know what all the options are to be able to use them effectively. Writing the job scripts for this command file parallelism, it can be hard. I actually wrote myself a little tool that writes them for me because it's, I got sick of trying to do it by hand. But now I have to maintain that tool. And in fact, we're changing schedulers, so I need to rewrite it. You have to do a step, hello kitty cat, where you run a single example of each step to see how much time and memory it takes, so that you can tell the scheduler how much time and memory it needs to allocate for each of those individual jobs. There's some nonlinear scaling of these problems also. So that calculating the freeze thaw step, I tried it originally saying, oh, I'll just do, 1 year to test. And that only took 5 seconds. But then you try to do 95 years at a time, and it takes 18.5 minutes, and it needs, 60 gigabytes of memory instead of half a gigabyte of memory. So there's definitely some nonlinearity, and you have to sort of try it out on a big chunk instead of just a little chunk, and you can't necessarily just multiply. And then I said, well, okay, maybe I can take the big files and split them into little chunks, and that just was gonna take forever, and so I abandoned it because it was taking way too long to try and do that. So then I said, okay, For our Science at Scale project, we've got this data in ZAR format also, which plays nicely with Pangeo. And we wanted to have some example notebooks. So I said, this would make a great example notebook that somebody can see how to use this data, how to interact with this data, and maybe, just take the notebook and reuse it for a new computation. So I wrote a Pangeo notebook to do the same computations. It's on GitHub. And so that's a nice thing, is that it's easy to share that way. And the workflow using Pangeo, so a couple things, I determined that after every major operation, it's important to print out the data structure and to plot a single time step to sort of, check it as it's going along and see that it's giving you sensible results, rather than, oh, I've gone through my whole computation and the array is filled with missing data. Something happened. And the numbers look really different because it's all about lazy evaluation. So it doesn't do any computation that it doesn't have to. All of these individual steps are very quick until you get to the end, and then it does the whole thing. So the general workflow is, you do a little bit of generic setup, you launch Dask, you load the data in, you do your calculation of the freeze thaw, which is, days where field 1 is above this threshold and field 2 is below that threshold. Do some aggregation, and then calculate the ensemble stats. And that all went really quickly. The times when it actually spent any time at all was just the time for doing these check plots, and it's only doing like just enough data to do that. It's doing like a single time step worth of computation. So the wall clock times are pretty quick. Until the final step, which is calculate the whole thing and write these out to file. It took 8.5 minutes of CPU, which is 14 some minutes of wall clock time. And the total time, start to finish, of running this entire notebook is about 15.5 minutes. One thing that's noteworthy is I did try using multi-file IO, and it, to my surprise, didn't speed things up really. And I should also mention that I was writing things out to netcdf because that's what the end user requested. They said, could you send me netcdf files? So I said, sure. And we probably ought to count the time spent on conversion. There's a little bit of preparatory time of converting netcdf to ZAR to get it to run more efficiently, and scale more efficiently if you're doing this on a big data set. That's about 9 minutes. Things that I found tricky, combining different data sets, so the tmin is in one ZAR data file and the tmax is in another ZAR data file, and combining those together was a little bit tricky. I had 2 different kinds of missing value. There's days when there isn't any data, just because, for this simulation, something went wrong and therefore there's no data here. Also, there are calendar issues. Some of these models use a non-standard calendar. So like with this simulation, there might be no data on February 29th because it uses a calendar that never has leap years in it. But there are also missing data because they're outside the spatial domain. This has all been interpolated to be on a common spatial domain. So, it's this weird sort of mushroom shape. And that means there's locations where there's never any data. And I wanted to treat those differently and I couldn't. So that was, figuring out the right way to handle missing values to get it to work correctly was a little bit complicated. Splitting the data set into these 3 ensembles based on multiple dimensions was hard because you can't use the group by approach. I had to by hand do a split, apply, combine approach, and I had to do that manually. Things that didn't work smoothly, there were some commands that would unexpectedly trigger a full calculation over the entire data set, like min count and things like that. And so there were, I found it a little hard to understand when a command was going to be lazily evaluated and when the command would sort of end up saying, oh, I need to compute over the entire data set. I had to mask the domain manually. I had to do that, figure out where there was no data and apply a missing data mask to that manually afterwards. Labels, if you want to use something like the model name as a label for the ensemble dimension, you have to convert it to a numpy array and to use that as a coordinate. And that was something that tripped me up for quite a while of like, why can't I use these strings as labels for one of my dimensions? And then when it came to the final step of writing everything out to netcdf, it was actually a lot easier to get it right because there's some variation from file to file. It was a lot easier to get it right just writing each file separately than trying to figure out how to do it using the multi-file data set capabilities. And especially when I found out that there wasn't any efficiency speed up, I said, well, then I'll just loop through and do it by hand. So overall, comparison in terms of total resource usage. The command line took about 20 minutes of CPU time to run. The Pangeo took about 24 minutes of CPU time. So, and I've got the breakdown here is that the merge step is 2 nodes, 2 minutes, 1.2 minutes of wall clock, about 3/4 of a core hour total. The calculating freeze thaw days was 60 workers, each using 70 gigabytes of memory, which is about 11.1 core hours total. Whereas on the Pangeo side, I never had to use, so the zarification step, which is a one-shot thing, we've done it, now nobody ever needs to do it again. That takes 40 gigabytes and 3/4 of an hour, but now that's an invested cost and nobody else will have to do it. And the notebook itself never needed more than 3 gigabytes per worker, and only 30 workers. So, the wall clock time on the command file approach was a little bit faster, but the Pangeo notebook was more efficient in terms of the resources it used. So overall, pros and cons of the two approaches. The command file approach, it's tools that have been around for a long time. And so if you've been using them like I have, they're familiar. It's pretty simple. There's very few prerequisites. You only have to install those two sets of tools, and it's a little bit faster. But you need a lot of expertise to be able to bang through these tools quickly, like I can. The reusability is pretty low. This is a very platform specific approach. If I were to do this again on a different supercomputer, I'd have to change a bunch of things. It's less resource efficient, and the scripting for dispatching these things to the scheduler for the supercomputer is kind of a pain. On the Pangeo side, it's a lot more accessible, it's more shareable, it's more reproducible. It's platform agnostic. One of the things we want to do is take this and say, okay, now I'm going to take this existing notebook and augment it a little bit to get it to go, hopefully, seamlessly from running on our systems to, with the data on Glade, to running with the data on an object store, to running with the data in the cloud. It's more efficient resource-wise. And then there's a bunch of nice stuff that you get for the integration with the Python ecosystem, which is, there's the visualization is all integrated into the Jupyter Notebook. There's a lot of feeds that you get for free to be part of the ecosystem, like that visualization I showed a few slides ago of one of my test plots. Do a X-array in it, sensible axes and images and all that kind of thing. Downsides are there's a lot of prerequisites. You have to manage your Python environment using Conda, which took us it took me a little bit of working with somebody else in Sizzle to figure out a Conda environment that would support this notebook. It's a rapidly evolving and moving target, so there's new capabilities that show up. And you go looking for information, and you find workarounds. You find Stack Overflow posts about workarounds for some issue that has now been resolved correctly, and things like that. And in terms of wall clock time, it was a little bit slower, but nowhere near enough that I would actually care about it. So I think going forward, if I were going to do this again, if it's something that I need to do quickly, I'm probably going to fall back to my familiar tools. But if it's something that I want to share with other people, and something that I want to make, something that I want to become a product that is going to be usable by other people, I think definitely Pangeo is the way to go. So that's my experience. Thank you very much.